If the cable of this elevator snapped right now, would you fall to your death? Most people think they know the answer. Most people are wrong. In the next few minutes, you're going to discover why elevators almost never fall, what actually keeps you alive hundreds of feet above the ground, and the single hidden limit inside this system that engineers fear the most. And once you understand it, you will never step into an elevator the same way again. If you like videos that reveal the hidden limits of engineering systems we trust every day, subscribe to the channel now, because this is exactly what Critical Limits is about. Now let's start with the fear everyone has, but almost no one understands. Elevators feel simple. You step inside, the doors close, you move up or down. But psychologically, elevators trigger something primal. You are suspended, you are enclosed, you have no control. And deep down, almost everyone imagines the same nightmare. The cable snaps, the elevator drops, and there's nothing you can do. That image is so powerful that it has survived decades of movies, myths, and urban legends. But here's the first truth. An elevator does not hang from a single cable. Modern elevators are supported by multiple steel cables, usually between 4 and 8, and each one of those cables alone is strong enough to hold the entire elevator at full load. That means that even if all passengers jump inside the cabin at the same time, even if the elevator is fully packed, even if something unexpected happens, a single cable could still keep it from falling. So the question isn't, what if one cable snaps? The real question is far more uncomfortable. What happens over time? Because elevators don't fail dramatically, they fail slowly, and that's where the real danger lives. To understand this, you need to understand what elevators are actually fighting against. Gravity is obvious, but gravity is not the enemy. Time is. Every elevator ride creates stress. When the elevator accelerates upward, tension increases in the cables. When it slows down, that tension changes. When it stops, the forces redistribute again. This happens thousands of times per week, hundreds of thousands of times per year. And every single cycle leaves a microscopic trace inside the steel. Steel feels solid. It feels permanent. But on a microscopic level, it behaves very differently. Inside each cable are millions of steel wires twisted together. Inside each wire are crystalline structures that deform slightly every time stress is applied. Most of the time, this deformation is elastic. The steel stretches, then returns to its original shape. But not always. Over enough cycles, tiny imperfections begin to form. Microscopic cracks, invisible damage, no alarms, no sounds, no warning signs. This process is called metal fatigue. And fatigue is one of the most dangerous enemies in engineering because it does not care how strong something looks. A cable can look perfect on the outside and still be dangerously close to failure on the inside. This is why elevators are not designed around a single layer of safety. They are designed around redundancy. If one cable fails, the load redistributes to the others. If tension changes, counterweights balance it. If speed increases unexpectedly, governors intervene. If movement becomes uncontrolled, brakes activate automatically. An elevator is not one safety system. It is many safety systems stacked on top of each other. But here's the paradox. The more safety systems you add, the more complex the system becomes. And complexity introduces its own limits. Let's talk about the counterweight. Most people don't realize that an elevator does not lift the full weight of the cabin. On the other side of the pulley system is a counterweight that weighs roughly the same as the cabin, plus about half its maximum load. This means the motor is not lifting the elevator, it is balancing it. The system is designed so that moving the elevator requires surprisingly little energy. That's why elevators are efficient. But that balance is also fragile. Change the distribution of weight, change the acceleration profile, change the number of cycles, and stress begins to accumulate where you don't expect it. Now let's talk about the single component that people fear the most and misunderstand the most: the elevator brake. Contrary to popular belief, elevator brakes are not there to stop the cabin during normal operation. They exist for one reason: to stop uncontrolled movement. If the elevator begins to move faster than a safe speed, a mechanical governor detects it instantly. Not electronically, not digitally, mechanically. A spinning device accelerates with the elevator. If it exceeds a threshold, centrifugal forces trigger the brake system. And when that happens, steel jaws clamp directly onto the guide rails. Not the cables, the rails. This means that even if all cables were somehow compromised, which is already extraordinarily unlikely, the cabin would still be physically grabbed and held in place. And here's something most people never realize. These brakes are designed to work even if the power is completely lost. They default to the safe position. No electricity is required to stop the elevator, which leads to another myth. Power outages do not cause elevators to fall. They cause elevators to stop, slowly, controlled, safely. So why do accidents ever happen? Because engineering is not about eliminating failure, it's about managing it. And every system has limits. One of the most dangerous limits in elevators is not vertical, it's horizontal, side loads. As buildings get taller, they move, not dramatically, not visibly, but measurably. Wind pushes skyscrapers sideways. Temperature changes cause expansion and contraction. The elevator rails are attached to the building structure. When the building moves, the rails move. The cabin must tolerate misalignment. The cables must tolerate shifting geometry. And this introduces new stress patterns. Not the clean, predictable tension engineers love, but complex multi-directional stress. This is why ultra-tall buildings require specialized elevator designs. Longer cables introduce more weight. More weight increases tension. More tension increases fatigue. At a certain height, traditional steel cables become impractical. This is why some modern skyscrapers use carbon fiber cables. They are lighter. They reduce self-weight. They extend the safe operating range. But even these materials have limits. Which brings us to the most uncomfortable truth. Elevators are incredibly safe. Not because they are indestructible, but because they are constantly inspected, maintained, and retired before they reach their limits. Every cable has a service life. Every brake has wear limits. Every component has a fatigue margin. Engineers don't wait for failure. They replace parts long before failure becomes possible. And when that process is followed, elevators are among the safest machines ever built. But when maintenance is ignored, delayed, or compromised, that's when the system becomes dangerous. Not suddenly, not dramatically, quietly. The most dangerous elevator failures don't involve free falls. They involve misleveling, unexpected stops, doors opening at the wrong time, small failures that indicate deeper stress inside the system. And this reveals the final paradox. The reason elevators almost never fall is not because they are simple. It's because they are paranoid by design. Every assumption expects failure. Every component expects wear. Every system assumes something will go wrong and prepares for it. That philosophy is what keeps people alive. And it's the same philosophy behind every safe engineering system on Earth. Aircraft, bridges, nuclear reactors, not strength alone, but controlled weakness, flexibility, redundancy, margins. So the next time you step into an elevator and feel that moment of fear, remember this: the system is not trusting the cable. It's trusting physics, redundancy, and decades of engineers who assumed something would eventually fail and planned for it. Elevators almost never fall because they were designed by people who never believed they were safe to begin with. And that is the real reason you're still alive when the doors open.